Buenos dias. Welcome back. Remember that we are discussing at this point the not performance management, maybe I should not think about management at this point, the performance of algorithms. So what we've done in the previous lecture is that we have done an empirical analysis of the three-sum problem. I remind you also that this three-sum problem is where we have an array of n numbers, and in those n numbers we want to see how many triplets we can form that will sum to 0. This is of course part of the example that I used to show how you would do analysis of algorithms. Hopefully at this point you are convinced why we want to do the analysis of algorithms, and this is where we will proceed, we will continue with today. I remind you also that we've done this empirical analysis, I've just said that, and then we've started off with the mathematical analysis. I've mentioned that it started off with the ideas of Knuth in the 1970s, that the idea is that you count the number of operations that an algorithm takes do, and then from this you have an estimate of how long it will take when you execute that. So what I've done there is in the previous lecture is we've gone through a couple of algorithms, count them up as a num function of n, and then we have the number of steps that takes place. Now, and then in the previous lecture we ended this with this notation, the tilde notation. I've said that you get these equations in terms of n for the input size n of how many steps an algorithm will do, and then we said, well, for large n we can ignore the lower order terms and then just keep the higher order terms. And then I've ended up with this technical definition of the tilde notation. So now let's take this and put this into practice with the analysis of our three-sum problem. So what I have over here is we want to count the frequencies, and of course this is taking place one time, so once. This is taking place n times. Now look carefully, we're not really interested in n plus 1. We don't write that out exactly, since if I have n plus 1, well, if n is really big, if you just add a 1 to it, we can just ignore it. So we throw away the lower order terms. Similarly over there, this loop is executing n squared over 2 times. We can even remove the divide by 2 times, since, and then of course we had an exact formula for this where we actually say it would be n plus 1 n plus 2 over 2, and so there's even a plus n and a constant over there, but when n is large, the n squared over 2 term will dominate. And similarly for this thing over there, you will see that the n to the power of 3 over 6 term will dominate. And so if you look at all these things, you will actually see that this one and this one and this one, they are the lower order terms compared to this one, and so we can ignore them, and we can say that our algorithm running time is n to the power of 3 over 6. So if we use this tilde notation, you will see that when we do analysis of this kind of way, then we eventually focus on the instructions in the inner loops. Since remember, if there's in the real inner loop that we have over there, then that will be the most times that this will execute the most times compared to the outer loops. And when we use the tilde notation, of course, that will then dominate our execution time. So just to repeat myself to make sure what we have the tilde notation. We could go down, we can add all the things up, but what we do is we ignore the lower order terms. We do this then for our algorithm, and then strangely, well, not that strange, we get 2n to the cube over 6, and that of course agrees with the empirical analysis that we've done in the previous lecture, where we've said it's a power law an to the power of 3. So at least the mathematics and the empirical estimates, they do agree. So again, we can get to the same result. Now we have this power law thing going on, this power law running time. So we say the running time of a typical program is an to the b. So where do we get this constants from? So b depends on the algorithm. I mean, if you just have these two loops and not the last loop, then it will be n squared times. But the a depends on many things. So there are a couple of things that's system independent. That would be actually the algorithm, and sometimes also the input data. Depending on how the input data looks, you might get different kinds of a sizes. Say for example, if I work with that where I add those numbers, I mean I will increment c and t only certain times, and that depends on how many triplets there are to start with in my input data. And if that increments takes a substantial amount of time, then of course that will be different for different sizes. So a also plays a role there. But then there are a couple of machine or system dependent effects. Here, for example, caching is an important thing. Maybe you don't know what caching is. So caching is when I have data in memory. Now memory is much slower than cache memory. And so what happens is if you have data that sits in the main memory, the computer can go and grab the memory data around the data that I grab near at this moment, put it in the cache memory. Then at that point when I execute it again, then the computer will just get the data from the cache and not the memory. And that's much faster. And so indeed I will show you, not this year but next year when you continue with computer science in 244, you will see some examples where if caching is turned on, the thing will just be much slower or faster, or depending on how the caching strategies work. Also the compiler, I mean the compiler can optimize the code, and that could lead to different execution times. In Java we have the garbage collector, and sometimes it runs, sometimes it will just not run during the execution of the program. And so depending on whether the garbage collection takes place or not, you might get a different execution time. In Java we have the so-called JIT compilation, just-in-time compilation, and that's where they compile the bytecode of your program to actual machine code, and that also influences the running time of your algorithm. And then of course on a computer there's just not one program, you have many other processes running there, and there's usually a fixed number of CPUs. And so if the CPU is used by some other programs, that might also lead to different running times. But the nice thing is that if we use this mathematical doubling hypothesis, and we can get the running time, an estimate for the exponent b, and then we can use experiments to determine a. Also the nice thing is in the mathematical framework we usually work in a system independent way, and that would still be enough to make predictions about your running time. So I actually want to summarize what we have so far. So we have had empirical analysis. This is where we measure our running times by stopwatch. We plot it, we fit a curve. It's relatively easy to perform experiments. I mean, no matter what kind of algorithm you're running, if you can run it on your computer, you can perform an experiment. And it's useful for prediction, but you cannot really explain what's going really deep under there below. You just have a number. On the other hand, you can do mathematical analysis, and that's where we count the number of operations. Now the things that I do so far, and we will do in class, they're kind of easy to count. But you've seen it already. I mean, we have those formulas that we've had that I said that you can prove by mathematical induction. And sometimes you really need advanced mathematics, really difficult mathematics, to be able to count that. And for that reason, mathematical analysis might be a bit difficult to do sometimes. The good thing is once you have had the mathematical analysis, you can use it for prediction and explaining. And the other important thing to realize is that mathematical analysis is independent of a particular machine or compiler. It will even work for computers that was not built before. You can really use it. It's in a sense, it gives you an abstract answer that you can use over all machines, even those that does not exist. I've mentioned that in the previous slide. The other nice thing about our empirical analysis, though, is that we don't have to launch rockets. We don't have to kill cars, crash cars. We don't have to kill rats. You can just do the empirical analysis yourself. Mathematical analysis, remember I said that you should do sometimes maybe hard mathematics. At least for the most important problems that we're solving, it's easy to calculate. So if you have a loop of this form, so you have this n, and n is increasing, halving every time you execute it, this will take log n operations. This is now at this point, it's really important that you go and count how many, make sure that you see how I get to log n. In this case, if you have a loop like this going through all the elements of n, well, that's clearly linear since you go from 1 to n. If you have two loops and you want to count the number of operations over there, well, this is calculating n times, and for this n times, the outer one is also calculating n times. So for each time this one is executing, this will execute another n times. So in other words, in total we have n squared quadratic operations. Of course, if you have a third loop there, it will be n cubed, fourth n to the power of 4, and so forth. Then an interesting thing that turns out many times is a combination of this linear one and this logarithmic one. So what you do is you recursively call gn, this function, by halving the size of n, and then you have a loop going on n times. So remember, if I halve this, if you believe me that this takes place log n times, it means that I will call log n times this function, and then once I've done that, I will have for each one also a loop of size n, and so we end up with n log n times for this kind of functions. And then finally I have the exponential times that I have over here. What I have here is that I run this for all the combinations of n, and this leads to 2n to the power of n operations. And these kind of problems, usually we cannot solve them for large values of n. We can do it for the small values of n, but for large values of n, you can't do that. So how do I actually see how that is exponential? What I would suggest is that you go and make the caller graph that we've done. So remember, you've done when you've analyzed the towers of Hanoi, you would have had something like that, and that would result to fn minus 1, and I would call it another fn minus 1. And then this one I would call with fn minus 2 and with fn until I get to fn 0. And then you have to count all the elements in this. You will see if you do this, go and write it out, that you get all the combinations that you will get 2 to the power of n entries in this tree. And that's why it's then exponential time. Just to remind you, so an example of an algorithm that you've seen already that takes exponential time is indeed the towers of Hanoi. N squared is insertion sort, is an example of n squared organized running time. N log n, an example would be merge sort, we will do that. And then log n would be a binary search, and this one I will indeed discuss later today. What I could also say is then that we can then classify these things, we give name to these things. So if I have a function of n, of a constant function, I say it's constant time. And the factor, if we use the doubling hypothesis, remember with the doubling hypothesis, if what I do is I execute the problem for size n and for size 2n, then I do this 2n over t2 over n, and I get this constant. And based on this constant, I can calculate this a n to the b, this exponent over there. Now if I look at this table, what I say there is if that constant is 1, then I have constant time, while it can also be in logarithmic time, it will be log n time, it will also be 1. In linear time, it will be 2, linear arithmetic time 2, in square time 4, and so forth. You will also see if we look at the running time, it's a log-log plot. Constant time and logarithmic time on the plot, log-log plot, will look something like this. And you can see really no matter how the size of the problem grows, in the case of constant time and logarithmic time, the time that it takes to execute this program does not really increase. With linear time it takes more time, with linear arithmetic time it takes more, but it's still not really going up. It looks what's going with exponential time. Even if you increase the problem size slightly, the time is really going up tremendously up there. And that's why, I mean, could you see if this thing is growing up there, if you have to go up all the until year, all the way until year, this number will be huge. I mean, you, in theory it will execute, but you will maybe wait until the end of this world, and perhaps even the end of the other world, and you will die, and many other people will die, and you will still wait for your program to finish. So there's a couple of consequences of this. So here I have the predicted running time if problem size increased by a factor of 100. So what will be the effect in the running time? So if it's linear time and it took a couple of minutes, then if I increase the problem size by a factor of 100, then it will take a couple of more minutes. Linear arithmetic, the same thing. If it's a quadratic solution, it might take several hours more. Cubic time, well, a few weeks more. And if I make an exponential problem 100 times more, well, it will be close to forever that you have to wait. Similarly, we have here the predicted factor of problem size increase if computer speed is increased by a factor of 10. So what happens is I give you a computer that's 10 times faster than the one that you currently have. And now I ask you, how much bigger can your problem be to take the same amount of time as it would run it on the slower computer? So if I've taken 5 seconds to solve a problem on a computer, how many times can I make this problem bigger if I use a computer that's 10 times larger? In the case of linear time, it will be 10 times larger. Linear arithmetic time, 10th time. Quadratic, it's 3 to 4 times. Cubic, 2 to 3 times. And look here. Even if I give you a computer that's 10 times faster, the exponential problem, you cannot make it larger. It will just still be the same one. That factor is still just 1. Now I want to put all these things into practice and discuss another problem, and that's the problem of binary search. Now this will just be an overview of binary search. In the lectures that we do next week, we are going to discuss binary search in even more detail and actually go and prove most of the things I will just mention today. So what's binary search? Well, the idea with binary search is I give you, maybe think of a telephone directory, and you want to find a particular person within the telephone directory. So you have to search through the telephone book in order to find it. So let's look at the easiest example. So I give you a couple of numbers like there. It's an unordered array, and then I tell you, well, go and find for me this particular number. And so what you will do is you will say I'm looking for the number 42. Then I would say, is 43 42? No. Is 72 42? No. Is 13 42? Is 84 42? And maybe I find it there somewhere, and then that would be where it's 42. I would return this index. Of course, in the worst case, I have to look at all the elements, and then I would realize it's not there. So in the worst case, I have to check all the elements. So it will take order n times. So it will take n times. It's proportional to the length of this array. Now the binary search thing is we assume that this array is actually ordered. So somehow that happened. and we will indeed show that I will teach you at some point how you would sort this efficiently as well. Now I have another demo here to show you what we do with binary search then. So with binary search, the key idea is that we have these two indexes, low and high, and then every time it's not there, we will half the problem size. So what we do is we have low index, which is this one, high index, we point to the end of the array, and then we have the middle index. And then we ask the question, say we look for 33. Is 33 greater than this middle point? No, it's not. So it must be in this half. So what we do is we scratch all those things and we move the high point to this one, since we know it's not there. Then we calculate the middle of that and we ask the question, is 33 greater or smaller than 25? Of course 33, the last time I checked, it's greater than 25, so we know it should not be there, so we can move the low point to that point. Then we say, is 33 greater than or equal to the middle point? So the middle point is 43, of course it's smaller, so we throw away those, and then we end up at this point, and boom, we found 33. So this is how we would do a binary search. And let me get back to my slides. We can actually go and implement this, and this is how I would implement this. This is not a recursive solution, this is in fact a iterative solution. So we have low, we have high, and so while the low point is still less than the high point, I get the middle point. If the thing I'm looking for is less than the middle point, well, then I move the high point one to where the middle point was, the point before the middle point. However, it's greater, then I move the low point to that point, to where the middle point was plus 1, and then at some point I will just return the middle point if I find it. Otherwise I return minus 1. So the question is at this point, how on earth, how many times does this take place? I mean, so how many times do I execute this thing? How many times will this execute? Now I have a proposition over there, and it says that binary search in an ordered array of size n takes at most 1 plus log 2n three-way compares. In other words, these compares that I do over there, it will be at most those. And the partial proof is after 3 ways of compares. In other words, after each time I compare it, the problem size decreased by a factor of 2. But this still doesn't answer how it is log n times. But the question is then, how many times can I divide n by 2 so that I can reach 1? Now I will prove this in detail in using mathematics at some point later this semester, in fact next week. However, for the moment you can do this kind of graphically, and you can see that it will reach log n times. So just do this and see that it will actually, if you count this, how many times it will happen, you will see it will approach log n times by doing a couple of examples in this tree. So the answer in this is about log n times. And since we know that this problem is halving every time, remember this demo that I had, it's halving the problem size every time. It must, we have this thing going on there. We know this fact that we're dividing by 2, how many times it will happen, log n times, and therefore as a result, this binary search algorithm takes 1 plus log square n 3 ways compares. So I have a question over there. If a credit card company needs to whitelist 100 million customers' account numbers, so in other words, you have to find those 100 million customer account numbers, and they can process 10,000 transactions per second. If they've done the simple sequential search, in other words, looking for the element in order n times, what kind of computer do they need? A toaster, a cell phone, your personal computer, supercomputer, and Google server farm. And the interesting thing is, if it's an order n time for this problem, it will probably need a supercomputer or Google server farm. Now my question is, if a credit card company needs to whitelist, 100 million customer accounts, same problem, processing 10,000 transactions per second, and they don't use the binary search algorithm, but they use, the sequential search algorithm, but they use the binary search algorithm. What kind of computer do they need? A toaster, a cell phone, your laptop, supercomputer, Google server farm, and interestingly enough, all of the above will be possible. Perhaps not the toaster. My toaster is still an analog toaster, so there's no processor in there, but maybe you own a toaster that has a digital processor in there, and then it will certainly be able to execute on your toaster as well. But for all the other things, it will do well. And that's the important thing that we should see over there, is that you have algorithms the brute force way, in a sense, the sequential search, that takes running time order log n, and you can count the number of steps. You can even go and then estimate the running time. And then we have a more advanced, a fancier algorithm, the binary search algorithm, that takes log n time, and that indeed allows you to solve a problem that cannot be solved using some fancy big computers. You can definitely solve that on even the simplest phones and computers that you have. So that concludes sort of my part that I've discussed on the analysis of the number of operations, the running time of your computer. But the next thing I want to discuss then is memory. So remember, there's two things in a computer that's important, or that's sort of a trade. There's many times a trade-off between the two things. The one is the running time. So of course, if your CPU is slow or your problem is too difficult to solve, you will wait a lot of time in order to solve this. However, there's a second thing that plays a role, and that's the amount of memory that you have in your system. Perhaps you've never had this problem, but I have run into this problem many times in my life, and that is where my computer will tell me, out of memory, I don't have any more memory. In other words, the problem that I'm trying to solve is so big that it cannot physically fit into my computer. So you physically have to go to the store and buy more memory or get a new machine that has more memory. And that's a real problem for many kinds of scientific applications. And for that reason, it's also important to have a mathematical model or a model for memory as you would have for running time. Since, I mean, it's all good to have a solution that can be solved in 10 seconds or in a millionth of a second, and it cannot be solved on your computer because you don't have enough memory. Of course, the other way is also true. If it's fitting on your computer and you have enough memory, but it's not fast enough, then you should be also a bit worried about that, since then you can also not solve it. So, what are the memory requirements for Java programs? So we have a couple of things that you should know. I'm quite sure, I'm actually 99.999% sure that Professor Lynette van Zyl would have told all these things to you, so I just remind you of these things. So a bit is the smallest thing that we can represent, so that's either a 0 or 1. Then we have a byte, that's 8 bits. We have a megabyte, that's 1,000,000 bytes, or 2 to the power of 10 bytes, and then a gigabyte. Then for different types, you have different bytes needed. So Boolean usually use 1 byte, and look, we actually throw away 7 bits. Since a Boolean actually need only 1 bit, but we allocate 8 bytes for it, 8 bits for it, a byte. If you continue with your studies, you will learn in Computer Science 244 why we would actually waste 7 bits and not just allocate that to the representation for a byte. Sorry, for a Boolean. And then for a byte, of course, it should be 1 byte. A char needs 2 bytes, an int 4, a float 4 as well, and the long needs 8 bytes, and a double needs 8 bytes. At this point, it might be a good thing to ask yourself, how much memory does my computer actually have? Okay, and then we have reference types as well, and that is then the reference types, so like objects. So for an object, there is an 8 bytes overhead apart from the memory needed for the instance variables. So for example, in the charge class, the amount of memory that I would use for a charge object is the following. Remember, this is 8 bytes, 8, 8, so that would be 24, and then I have an 8 byte overhead, so that leads then to 32 bytes. The other thing to remember is that a reference to an object is a 4-byte pointer. Also note that I've listed there it's a 32-bit machine. So remember, you probably haven't done that. So we have different architectures for machines. We have what we would call 32-bit machines. That is, our data bus, the operation size is, well, not the operation size, but the data bus is 32 bits wide. So in other words, we have literally 32 wires for the address lines and also for the data that we have. We can think of it as literally wires. The 64-bit architecture, they have 64 wires there on the bus, and so that's where this is coming from. Again, this you will learn in detail in Computer Science 244 next year. So then if you have the 64-bit architecture, which is kind of the common thing nowadays, then these numbers slightly change, but you can always go and look that up. Then in the case of the arrays, we have an interesting thing. So we have a 16-byte overhead for just using the array data type. So for example, the length of the array is stored in the array itself. And then of course you need the number of memory still for the actual data that you store. So say for example I have an array of int. Well, then of course I have the 16 bytes overhead, and then I have n elements in the array, so I have 4 bytes per integer times n, so I have 4n plus 16 bytes that I use for an array. Then for a double, I have similarly, I have there the 16 bytes overhead and then 8 bytes per double, and there are n of them there. In the case of the charge object, we have the 16, the 36, like the 16 byte overhead for that, and then we have the references to this charge objects. Then we have this int array over there. So let's see if we can work that out. So remember, an array of int, so int a of size n would have 4n plus 16 bytes of memory. Now I have an array int a, and let's make it of size n by n. Now remember, the first array, how Java is storing this is it's storing references to this arrays of size n. So the first element in this array is pointing to this one, it's pointing to this one, it's pointing to this one. So we end up with, for this array, we need 4n plus 16 bytes. And then for each one of them, we need another plus 4 plus n times 4n plus 16. And I just hope this add up to 4n plus 16 plus 4n square plus 16n, and that's 4n square plus 20n plus 16. I was really fearing that I don't get the right answer, but look, it is the right answer over there. And similarly, for a double, we can do the same thing, and I really encourage you to do this. Just be warned and be careful. I did this when I prepared this lecture, and then I got it wrong, because the one thing you want to do immediately is to say, but for this array I would need 8n plus 16 bytes, and then you do the same calculation. But of course that's wrong, since here in this array we're actually just storing references to these smaller arrays, well, they're also of size n, to this arrays of type double. But the point is these are just references to objects, and references are not 8 bytes, they are 4 bytes. Remember, a reference is 4 bytes, and these are just references to the arrays where the actual data is stored. So that's why you get then this particular value over there. And for the string, well, I encourage you to read the complete section in the textbook on how you would store a string object. But it should be clear how to get to this number as well. That's the number of bytes it's storing. So a question that you can try to answer now at this point is what's the biggest double array that I can store on my computer? Remember, as in the case of the frequency counts, of how many times for the running time, we can do now the same thing, and we can count the amount of memory that my program needs. And we can even do the same notation that we then say, okay, but the lower order terms we can ignore, and we keep the higher order terms to classify how much memory my system will need at this point. So now I want to do some summary, and I want to ask the question. Remember, our question is how can I evaluate the performance of my program? And then we said that we will do it one of two ways. We will either do it with experiments or with mathematical analysis. And for this whole approach, we actually followed the scientific method. Remember, the scientific method was about forming a hypothesis. We want then to design experiments, and then we verify those things and validate it, and we have actually a discussion and thinking about the hypothesis again. And for this kind of analysis, we've followed indeed the scientific method. And so the question that you can answer now next is what if it's not fast enough, or I don't have enough memory? So what should I do at those points? Well, you should understand why it is the case, and now I've given you a set of tools to do that. You can do the running time analysis in case your program is too slow, or alternatively you could do the calculations for the memory, and then you can understand why. At this point, you could go out and buy a new computer, or more memory. If your program is, for example, an exponential time going on, well, at this point it will not really help, since you cannot do it on a new computer, will not make a difference. So then you have a bit of a problem. So what are the other alternatives? Well, the other alternative is you should learn a better algorithm to do and solve this problem. We will discuss some of the nicer and better algorithms at this point in this semester that's remaining. And then next year in Computer Science 214, and actually throughout your computer science career, but in particular 214 next year, there you will be taught new algorithms that is indeed fancy and will help you to solve this problem faster and more efficiently. If that is not working, well, then we get to the world of research, and then you just have to discover a new algorithm. Now at this point you also have the analysis of running times to your disposal, and the question is, when should I do this? Now you should always be aware of what's going on. In other words, you should always pay attention to running times. You should never just write a program from today onwards and not think about running time. You should think, how long will this take to execute? And just bear that in mind, since if you don't do that, then you will just write bad code, and you will also not be able to understand and what's going on underneath if you don't take those things into account. So rule number one from today onwards, always think about the running time of your programs when you do write them, so that you can understand what's going on there underneath. However, there's a warning that comes with this. Don't optimize your program and try to implement every fancy method that's out there. As it is important to always think about the running time of your program, it's also dangerous to just every day implement the more complicated code to make a savings and an execution time. Many programmers fall in this pitfall that they try to use the most fancy techniques in order to solve a problem. And what you will see in reality is many times that it's not necessary to optimize all your code, but only a certain part of your code. You would go and make that faster. So premature optimization, premature implementing always the fancy thing is also not a good idea. But it's this trade-off that you have to get right. So that's the thing to keep in mind. Just there at the end I have this a table over there with this trade-off of a better algorithm versus a better machine. So of course, cost-wise, if you buy a new machine, it's much more expensive than developing a new algorithm. Of course, if you have a new machine, all your algorithms could run faster. In the case of a better algorithm, only that particular problem will be solved faster. However, improvement of a new machine, it's a quantitative improvement. I mean, it will take some time longer, shorter, but in the case of a better algorithm, there will be a dramatic improvement in the quality of your algorithm, in the running time of your algorithm. So this brings me to the end of this lecture, where we've discussed performance. In the next lectures, we will discuss some other fancy techniques of programming. In particular, I will discuss dynamic programming, and that's a way that will allow you to actually solve certain types of problems much faster, so in a more fancy way. I mean, I said you can have a better machine or a better algorithm, and I will teach you then one technique, and also throughout the rest of the semester, how you can do this much better than just do it in the brute force way. I do thank you for your time.